I did have a life before C60, which came out of the blue, but I'll talk about various aspects of chemistry in nano and outer space. Let me just see whether there's some sound on here. Just to check. Okay. All right. That's to wake me up as well as the rest of you. Okay. And what was it? I was working, and I think it's important to realize that research can go in many, many ways. And I was working on carbon-sulfur double bonded, carbon-phosphorus double bonded, carbon-phosphorus triple bonded species, and particularly those molecules at the bottom there. Now, what interested me, perhaps in the early phase, is shown by this molecule, which is my favorite molecule. It's not C60. I hope it looks like something to some of you. Anybody, any idea? Yeah? What? A dog, yeah. It's my dog. Okay, it's got a red nose. If you look at the microwave spectrum, you can show the dog shakes his head and looks at his tail. Not only that, my dog, whoops, daisy, go back to this one, and it's a bit temperamental today. It undergoes internal rotation, and it's been drinking, and if you've been drinking too much from your dog, you desperately need a lamppost. Now, the point about showing you this is that molecules are flexible. They're not rigid. And that's really something that I think is important, more important in the 21st century. And of course, we know that carbon dioxide is, actually, could we have some of the lights down because there's too much light? Is it possible to do something about the lights? I don't know. But there's a lot of light bleeding onto the screen. So I was interested, and I think it's important to realize how research carries on. I was interested in flexible molecules. And, well, okay, they're either all off or all on, are they? Okay, there you go. Well, maybe you better have them on. And the spectrum that started rolling was this molecule, which I developed an undergraduate project with David Walton, my colleague at Sussex, who had made carbon chains with as many as 32 carbon atoms. And what David had done was produce this oxidation decoupling process using copper catalysts to produce long carbon chains. And that was the molecule that we made. At the same time, radioastronomy really came on song. This molecule, HC3N, and we'd made one with 2 extra carbon atoms, was detected. So I wrote to Takeshi Oka, my former colleague at and I said, we got the frequency, and he wrote back, thank you for your letter. Yes, I'm very, 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 very much interested in your molecule. The same number of varies as there are carbon atoms in this particular molecule. And that led to the detection by radioastronomy of these molecules in space. Now, this is a really important aspect of what I want to talk about at this conference, is that you don't know where you're going. I mean, not all those who wander are lost, as from the Lord of the Rings. But the important aspect is to do what interests you. And we used this telescope, and we were able to show that the molecules that are rotating, you can detect the frequency of rotation by radioastronomy, and we were able to show that in space, all these molecules were in the space between the stars. Okay. Well, we were excited, and of course, okay, it's an alert here, let's get rid of that. And I show this because I used to have some hair, as you can see from this particular picture. And it got into the newspaper, and they said the chemicals were discovered thanks to Canadian work in radio astrology. I hope some of you know the difference, but you never know. The newspapers usually don't. Anyway, we use spectroscopy. Okay, let's pull that down. Okay, whoops. Oh, sorry about this, folks. Very odd things are happening. I want to get back to here and get to there. And then a star was discovered, a carbon star, IRC 10216. And in that star, our carbon chains were discovered. They were being pumped out. So there was something interesting in the star, that the carbon chain molecules were being created in that and being pumped out. And I was interested in what was going on there. Wow, is it sensitive today? All right. Okay. And by chance, I was visiting Rice University. Bob Curl was my friend, and he suggested I go and see Rick Smalley. And what Rick had developed was a brilliant technique where you vaporize aluminium under argon and produce clusters. And whilst he was telling me what he was doing, I thought, well, why don't we change the silicon and silicon carbide for graphite and produce the carbon chain molecules, and so simulate the conditions in this star. So that was a very simple idea. Nothing more, just simulate the conditions and see whether we could produce the carbon chain molecules. And that led to the C60 molecule. Let's go back to it and just see what actually was involved in that. Okay. Let's go back to this. These are the students, Jim Heath, Sean O'Brien, Yuan Liu, and what we detected was an incredibly strong signal for C60, and also C70 as well, okay? And that was unexpected. Now, we weren't looking for it. There was no idea that this was an important experiment. This was just a back burner experiment, which was interesting to me, and we managed to show that. I wrote C60, question mark, C60 huge, C70 also. We decided to celebrate, which is what you do, and we went to a Mexican restaurant, sitting at this table, discussing what was going on. Somehow graphite sheets had done something special, and this is the floor of Bob Curl's washroom, the loo, and I would sit and contemplate this floor. Well, every morning, what was so special about it? 6 is special, 24 is special in symmetry. You're looking for some sort of pattern, okay, some symmetry pattern. Well, it turned out that I had a graphic art magazine, Graphis, Expo 67, and this particular image was in my mind. So here again, it's not necessarily just JACS and nature. It turned out this image was very important in deciding what was going on. And I suggested we get Buckminster Fuller's book from the library, which we did, and then try to understand what was going on here. And I also remember that I had a star dome for my children, which had not only hexagons, but also pentagons as well. And that night, Rick put together hexagons. They didn't work, but when he remembered, I said, you know, there are pentagons in this structure. In he came the next morning with this guy, and it has 60 vertices, and we were just ecstatic. Okay, so that's the first part of the story. If you want to know where the name came from, well, I named it, and Rick wasn't very pleased. He said, as he says here, he'd overcome any initial reservations he might have had on my proposal of the name. And then he said they found it appropriate because it conveys in a single word so much information about the shape of the molecule. Anyway, if you want to blame somebody for the name and you can't say it, if you're from Japan and difficult with FLs and Rs and things like this, it's my fault. I take full responsibility. So that's where the name came from. Okay, there's a whole load of chemistry, maybe 1,000 papers a year on the chemistry of C60. What I like about science is that what we have here today is an international group of people. No other discipline has that internationality, inter-race, whatever color you are, whatever you believe. Whatever happens in your lab in England or the US has to happen in Japan or even on Mars. And that's the group, and somebody will recognize this fellow, Umberto. This is your brother, Mauricio, when he was in the UK. A few years ago, I retired, and then now at Florida State, and I thought I'd show you my colleagues there. Steve came from the UK, Darryl Artrees came from the US, Prashant from India, Nicole Pugno was a visitor from Italy, and Paul Dunk is an American. This guy is Paul Dirac, who spent about 12 years at Florida State. I really can't get him back into the lab. He seems to prefer to sit outside in the rain and the sun, so I thought I'd put my hat on top of it. Okay, so there you go. Now, the question now is, what is nanotechnology? Well, for me, it's basically chemical self-assembly. And a good sort of thought about it is, one day, shall we be able to create a computer by bottom-up assembly? Well, it's already been done because your brain is some sort of computing device, and it's been created by nanotechnology, atom by atom, molecule by molecule, protein by protein assembly of a complex system, okay? Because that's nanotechnology, not just creating small things, but controlling the assembly at the nanoscale and building up complex systems. And on the basis of that, one of the little projects that I had at Florida State when I went there a few years ago was based on this beautiful ferrite core memory. What I like about this is I can understand it, okay? Basically, half the current goes through that wire, and half the current needed to magnify goes at the same time, and then if you do it at the same time, you magnetize the core. It's nice and simple. I understand what's going on. I don't know what's going on inside these computers, my mobile phone and all these other things, but I understand this. So here are some of these things, and we can see them. And in fact, if we go to this particular experiment, the question was, can we create something similar on biochemistry? And these are some of the nickel clusters. They're not magnetic, but it's the first rung on a ladder, a two-dimensional array of metal clusters. If we can create this, a two-dimensional array by chemistry, and of course we have to address them, but it should be possible to do that. And so that's one of the first sort of little projects I had. It's 100 rungs on the ladder, and we're on the first rung. But nevertheless, it should be possible at some point in the future. And here's Prashant, Naresh Dalal, and Tony Cheetham, my colleagues on that too. Now, I thought I'd say something about research, the way that I do it. And I go back to when I was a kid at school. When I was 7 years old, my name was Kroto, and I thought I hope you can read this. Miss Bowker thinks I'd better write and tell you that we're not at all pleased at the way Harold has been working during the last few weeks. It says he is very fond of play. Okay. Now that's interesting because my teacher wasn't very happy about the fact that I like to play. Now, I hope we can show this. We'll see, it should be possible.
So I decided I'm going to do things only for the fun of it. And only that afternoon when I was eating lunch, some kid threw up a plate in the cafeteria, which has a blue medallion on the plate, the Cornell sign in the cafeteria. And as he threw up the plate and it came down, it wobbled and the blue thing went around like this. And I wondered, it seemed to me the blue thing went around faster than the wobble. And I wondered what the relation was between the two. See, I was just playing, no importance at all. So I played around with the equations of motion of rotating things. And I found out that if the wobble is small, the blue thing goes around twice as fast as the wobble goes around. And then I tried to figure out if I could see why that was directly from Newton's laws instead of through the complicated equations. And I worked that out for the fun of it. And this rotation led me to a similar problem of the rotation of the spin of an electron, according to Dirac's equation, and that just led me back into quantum electrodynamics, which is the problem I've been working on. And I kept continuing now to play with it in the relaxed fashion I had originally done, and everything is just like taking a cork out of a bottle. Everything just poured out. By the way, in very short order, worked the things out for which I later won the Nobel Prize.
Well, the point that I'm making is that to be creative, you do have to have the freedom to create and not have a burden of responsibility. And that's an issue. And I think it's an issue today more than anything else. Now, sometimes you have a wow moment, and I thought I'd show you some photographs that Margaret took in this square in the town of Delft, which is Vermeer's town. We were sitting at this table, and there's actually a buckyball up this, and little children would come up to the table. This was one of them, and I tell you, his tongue never went in, okay? It was really fantastic. And his sister wanted to make one, so she made one, and little kids came up to the table. And I want you to look at these kids. They're not thinking about, winning prize or doing something important. They're being really creative. they're building things. Now, it turned out the first customer was this little girl, 3 years old. And we knew there was something special about this little girl. And Mum said, you know, can she do this? And Margaret, who's over in the corner here, said, yeah, well, let her try. And I wanted to look at this. This kid was just totally concentrated making up these models. And we go around the world and do workshops with small children, but we'd never seen anything like this for a 3-year-old. I've had 8, 9, and 10-year-olds who could not do what this little girl was able to do. But when we looked at the final picture, it was just spectacular. Just look at this. This is the pure joy of creating something and really sensing it. You can't script it, okay? An actor can't do that as well as this. Now it turned out I had something similar. I was like a little boy, focused on it, and I was trying to make C32. And I was sitting at, I was just doodling, playing around with it. And I counted it up and I realized I made C28. And my hair stood on end because I knew we had a very strong signal under certain conditions of C28. And I was looking at this and realized that it would be tetravalent. But if you added 4 hydrogens, you would retain the aromatic rings on that structure. And so it would be a sort of tetravalent superatom. And we've been looking at these and putting titanium on the inside. And in fact, Rick Smalley's group, about 5 years after I predicted it would be tetravalent, showed that you could put uranium on the inside. And uranium is tetravalent. Now we've been looking at that again because we got fantastic resolution at Florida State because we have the National High Magnetic Field Lab there. And Alan Marshall has developed FTI ICR mass spectrometry. Now, this is the mass spectrum, and this you see is C27. That is uranium C28, okay? And just look at it. It's the strongest feature on the whole block, okay? So if you put uranium in and vaporize carbon in the presence of uranium, what you get basically is uranium C20. We'll try and see whether we can extract it. But these are actually early days at the moment, okay? We've also been looking at endohedral fullerenes, and if you put potassium in, then C60 and C70 are the strongest features, okay? But if you go to group 2 metals, what you find is that 50 and 60 are the strongest features. And if you go to group 3 metals, it's C44, 50, and 60 is not so strong at all. So we're going through the whole periodic table to show what's going on there. And here are my colleague Paul Dunn, fantastic student, who's been doing this work together with Chris Hedrickson, Nolan Kaiser. At bottom is Alan Marshall, who developed this fantastic resolution, and Nori Shinohara and Nagoya, with whom we're doing this work. Okay. Now, some years ago, I had an idea that how metal catalyzed nanotubes were formed. And if we look at the electron microscope image of these here, you get a cross-section like this, okay? But sometimes the central tube is sealed off, a bit like this. And what you observe is, in electron microscopy sometimes, is something like, here's a metal particle, and here's a little igloo of graphite, okay? And I wondered whether what happens is that in a crystalline carbide or a metal carbon species, surface reconstruction could actually produce a graphene sheet, okay? And that was the idea behind that. And then Umberto and Mauricio, and Umberto's here in the audience, sent me this beautiful sort of results that were obtained that they had obtained with Florian Banhart in Darmstadt. Again, let's look at this electron microscope image. And if you see a flat meniscus, this is the metal catalytic particle. Here are the cross sections of the nanotubes. Now watch that flat meniscus becomes curved, and then you see this line. You see that line? That's a graphene sheet lifting off it, And if you actually get a whole load of those. And in fact, I think this should work. Let's just see this. Okay. And there you're seeing the birth of a nanotube, okay, in real time. Fantastic set, and I'm very grateful to Umberto, Mauricio, and Florian for sending these particular pieces of data. Okay, and here is an image of what appears to be going on. All right, let me go on because the time is short. I want to come to the last part of what I want to say. One of the things that has been extremely puzzling for over 90 years are something called the diffuse interstellar bands, the DIBs. These were detected about 1919 and certainly 1922 and shown to be interstellar. That means as you look at a star with a spectrometer on a telescope, you see absorption lines. And what you see in many, many stars are these white absorption lines. Not a single one has actually been identified. We've got millions of compounds, and yet these look as though they're molecular, and they've never been identified. Now, they're well identified, or their frequencies are well known. Here's a set of them. Here are some others, 578T, 5797, 5850. Now, there's not a single molecular spectroscopist that I know who hasn't puzzled about these. There's not a single astronomer I know who hasn't puzzled about this. So it's nearly 90 years that this puzzle is going on. Now it seemed to me that when we discovered C60, it was the third man. I mean, there's graphite, there's diamond, and there's C60. It's been lurking around. We should have detected it definitely in the 60s. There were mass spectrometers who were around that could do it. I don't know what the combustion labs were doing. Mitsubishi built a company, a sort of factory, and they make C60 by the bucketful by combustion of methane. Okay? So what have the combustion labs been doing all their lives? They didn't discover C60, yet you can make it from methane by the bucketful. Okay? Anyway, it's been around. Now it seemed to me that the possibility is that C60 was responsible for these lines. It's been around, lurking around, you couldn't easily find it. And one thought I had with Mike Dura is this one here, that you would have atoms stuck to it. See, C60 will be a soft landing in a bimolecular association. So if sodium comes in, it will sort of move around, vibrate or rotate around and get rid of the excess energy that way. Not only that, it could give rise to a very strong charge transfer band, such as this, C60, the charge transfers from the sodium to the C60. And that would have a jump of about 5 to 7 angstroms, which is 5 to 7 angstroms greater than its standard moiety chromophore, which is about 1 angstrom. So it'd be about 25 times stronger, or maybe 50 times stronger than expected. So there you go. Our suggestion 1993 or so was that C60 was in space. I thought of it as the third man. Some of you might know the film The Third Man, Orson Welles lurking in the back streets of Vienna. So for me, C60 was the guy lurking in the back streets of the galaxy, and not just the back streets of Vienna. Then in 2010, the Spitzer telescope, shown here, produced an amazing result. This is an amazing result. Here is the white is the spectrum of a star, a carbon star, carbon planetary nebula. The red is the spectrum of C60. The blue is the spectrum of C70. All the peaks that must be there are there. It's unbelievable. The only thing in the infrared, if you're a chemist, you know that you use the infrared to identify the fingerprint region. There's nothing else identifiable there. What is going on? Here is a star with the conditions producing the only thing you can actually identify as C60. Well, it seems to me, if you think about it, all your carbon atoms were made in a star like this. many of your carbon atoms once were a C60. So you really, once upon on the way here, you were a C60. Well, that's interesting because I'm going to show the end of this film. Here's Wolfgang Kretschmer, who with Don Huffman and their colleagues Lowell Lamb and Kostas Fosteropoulos extracted C60. It's a great guy, and they did a most beautiful piece of work. I think what they did was one of the most beautiful, elegant pieces of chemistry that was done in the 20th century. But anyway, this is the end of the film.
I believe it is there. And it would be rather nice to feel that, in fact, we were on the right track. There are some interesting features in space, and C60 certainly can fit them better than any other proposal that has been made up to now. I'm a believer, and I think ultimately we'll find that it is there.
But others have said that C60 is nothing like a match for the diffusion stellar mass.
They're wrong.
Thank you very much. Take my
I invite Dr. Yakanti now to give a trophy to Dr. Harry Pratt.